Yes, so now we have the final talk of this joint session. The speaker is going to be José Manuel Carmona, who is chair of this cost action.
Thank you, Julia. Okay, I would like to introduce the network of this cost action to those people who don't know it or even don't know what a cost action is. This cost association receives funding from the European Commission, and the main tool at what they are called cost actions. Cost means cooperation in science and technology. So the main objective is to form new communities to cooperate in this sense. And I would like to show that the present network has helped to have new opportunities and new challenges in the field of quantum gravity phenomenology. The title of the action is written in this logo. It was Quantum Gravity Phenomenology in the Multimessenger Network. And yes, you can click. Okay, this was reflected in the main aim that defined the cost action. It was to investigate possible signatures of quantum gravity models in the cosmic messengers. And in order to do that, the key point was to establish a close collaboration between different communities, between theoreticians on the one hand, and between experimentalists of the different cosmic messengers, because also these experimentalist communities are rather different and use different techniques, different apparatus, etc. No? So that was the objective, and in fact, we managed to join quite a large network. Presently, there are 325 researchers from 44 countries. 28 of these countries are what are called COST members, and 2 near neighbor countries. And the structure of the action tried to reflect this main aim and this cooperation. Working group 1 is mostly a theory oriented working group. Working group 2 tried to establish a connection between this theory side and the different experimental working groups, which were dedicated to each of the 4 cosmic messengers: gamma rays, neutrinos, cosmic rays, and gravitational waves. We have had during these years, these 4.5 years that the cost action has lasted, a number of different activities. We can remark here there was a kickoff meeting in Barcelona in 2019 when the action officially started. And then we have had several annual conferences. This is the 4th of them. There have been also some online meetings. I want to remark here the one celebrating the 20th anniversary of double special relativity. The discussion session about the LASO results that were presented in that year, in 21. And we have had some different workshops, and especially 3 training schools, because this was also a main objective of the action, to form a new generation, to train a new generation of researchers, because usually the field is quite interdisciplinary. Apart from these meetings, there are other tools associated to the cost action. One very important is what is called the short-term scientific missions. We have had 35 of them, and this has allowed researchers to visit other groups and to initiate collaboration, because precisely one of the main goals. Perhaps I want to remark some collaborative projects that have taken place within the action. One is this review paper on quantum gravity phenomenology that Giovanni already mentioned before. There is also a database with experimental bounds on quantum gravity searches. And we are in the process of writing a white paper to conclude the action. And also there is a focus issue in the classical and quantum gravity journal. The lecture notes of the training school are going to be published. In fact, those of the first training schools are already being published in POS. You can access them through the webpage of our action. And apart from this, we have had a number of outreach activities, diversity initiatives, and presence in social areas. Well, all started, as I was saying, with this Barcelona kickoff meeting in 2019. The title of, or the main topic of this meeting was this question: what would you like other participants to know about your research? In fact, I think in this meeting, many experimentalists knew for the first time or learned for the first time about DSR theories, because most of analysis, in particular in time delays, have been done in Lorentz evaluation scenarios. Also for theorists, when they learn how experimentalists really do the analysis procedure, for example, in this kind of time delays. This was very timely. I didn't press the right button. Very timely because, in fact, in 2019, in this year, there was this first observation of TeV, tera-electron volt emission, from a gamma ray burst by Cherenkov telescopes by MAGIC collaboration. This was a very important result, where MAGIC collaboration was able to put, thanks to this gamma ray burst, very strong constraints on the scale of quantum gravity, not as competitive in the case n equal 1 to the gamma ray burst that Giovanni mentioned of 2009, because of the distance. No? It was more near. But the energy of the highest gamma rays, the highest photons were larger than that gamma ray burst. So for the case n equal 2, for example, the limits were longer, were higher. Thanks to this cooperation between theorists and experimentalists, well, there have been already some DSR modeling, for example, or some proposals for DSR modeling, including the strategy of this first combined LIV study with Cherenkov telescopes, what is called this Gamma LIV working group. Right from the beginning, we were also conscious and started discussing about some critical aspects of these time delay studies. I'm referring here to these intrinsic time delays that well, we have been going on with this discussion. And in fact, yesterday we had several talks concerning this topic and the possible strategies to deal with this. So I want to remark here that all this phenomenology, this LIV and DSR phenomenology, involves three levels, no? which refer to the production, to the propagation, and to the detection of these messengers. And this involves astrophysics, this involves theoretical modeling of these effects, and of course experimental analysis techniques. So all of these different subfields are connected and are relevant to put limits on quantum gravity phenomenology. Also, I want to point out that already at the beginning of the action, there were some divergent findings concerning some theoretical analysis which report evidences of some photon time delays. This was also discussed within the action. This met with some skepticism from experimental collaborations, mainly because they are analyses that don't really take care of all the details of the instruments, for example. But also, it was recognized that there are some important points here that, for example, to combine different population of sources to combine studies. So this is something that has been progressing and it is going on. Okay, I would like here. Sorry. Okay. At this point, I would like to remark that the quantum gravity phenomenology has been usually associated to the Planck scale, but is this necessarily so? In some models, quantum, the Planck scale is natural scale, but in some models, one could consider lower scale, which are below Planck scale, perhaps many orders of magnitude below the Planck scale. Which are the limitations of this? Well, in the case of Lorentz device modulation, one can in fact explore the Planck scale. We have sensitivity. This is mainly because of two reasons. If you consider the propagation of cosmic free massless particles, time delays is a mechanism of amplification because of the distance they travel. Also, from the point of view of interactions, kinematic thresholds are modified in LIB in such a way so that the modifications are important when the mass terms are of the order of the new corrections. And this may happen, in fact, at energies much lower than the Planck scale. So that's why we have sensitivity to the Planck scale. But the situation is different. It's completely different in a TSI scenario. Here there is a relativistic principle that, and this changes the situation. For example, concerning the kinematics, there is an extra ingredient, which is the composition law, besides the modified dispersion relation, and that makes lose sensitivity to the Planck scale. So that the modifications, the relevant modifications only happen at the scales which are close to this high-net scale. Also, the propagation of massless particles can change and impact they may or may not present time delays depending on DSR model. So one needs to take also to have in mind this. Okay, in May 2021, we had this fantastic news. LASSO opened what we can call the PEV window to gamma rays. And as I mentioned, our action organized an online session with members of the LASSO collaboration to discuss this. So the main message was that our galaxy is apparently full of neutrons. Well, as Giovanni also mentioned, the key point here is to try to determine the exact location of these sources. Because, for example, because of the universe lack of transparency to high-energy gamma rays, one could not in principle explain within special relativity the arrival of very high-net photons or PV photons from outside our galaxy. So in fact, this offers also some challenges and some opportunities for this community. Some of them are the following: the uncertainties that we have in the photon backgrounds, in the extragalactic background light. Also that the Lorentz violation studies of this process in which high-energy photon loses energy when colliding with this background photon. Well, these studies rely mainly on kinematic modifications, for example, of the threshold of the reaction. But there are other modifications, for example, in the cross-section of this process. And really, there are not exact computations of this projection, but some assumptions, some dynamical assumptions are made in this case. Here I want to remark that the superluminal scenario is strongly constrained, not only because this is more favored, but also because the photon becomes an unstable particle. The superluminal scenario, however, could explain these apparent anomalies also that Giovanni referred to. And DSR model here without time delays, in fact, may allow for correction in the transparency of the universe with a high energy scale, which can be significantly below the Planck mass. And this is something that has recently started to be studied. This is just a result from this paper. This result is, well, in this plot, you have the quotient between two fluxes. The flux in a DSR model with respect to the flux special relativity. So the flux to special relativity corresponds to this horizontal line. And you see here, for a lambda scale, which is of the order of the end of the spectrum that LASSO measures, that is of the order of PV, you have corrections to the flux, which, depending on the energy of the photon, may enhance the special relativistic result or maybe suppress it. This is quite different from the LIB scenarios, which is either superluminal or subluminal. So DSR can qualitatively change the behavior also of LID scenarios. Well, also in 2021, we had what we can say the evidence, some evidence of the Glasgow resonance. The Glasgow resonance, I recall to you, is the production of a real W with the interaction of an antineutrino with an electron, for example, in the ice. And the ice cube had observed an event at the energy of this resonance, which is 6 PeV. This has been the highest energy neutrino observed by ice cube. Well, this is very relevant, of course, for LID studies, because in fact, at that time, there was some surprise that we hadn't yet get some signals of this Glasgow resonance, which enhance the cross-section. And in fact, LID had been proposed as a possible explanation for this apparent cutoff in the high-energy neutrino spectrum. This is because superorbital neutrinos can decay. They become unstable, and they can decay emitting electron-positron pair or neutrino splitting. That is here, this process here, that is further more neutrinos and with different flavors. One can try to connect neutrinos with gamma rays in this multi-messenger view. And well, as it was mentioned, IceCube and Antares has unsuccessfully tried to find correlations between neutrino events and GRBs. Well, we have seen that some claims about possible correlations with large enough time windows. One, of course, in this analysis should take into account what I said previously about neutrino decays. So one could ask whether this is compatible with the previous neutrino decay process. And for this, recent analytical calculation for neutrino decay widths and the probability distributions for these decays can be relevant, maybe relevant to explore these LID scenarios. This could also modify the standard flavor composition at Earth. So this is another aspect to take into account. We have very recent results from IceCube a couple of weeks ago that in fact seems to establish a correlation between gamma rays and neutrinos of much lower energies. But of course, without identification of the source, which will be the next challenge. Concerning cosmic rays and ultra-high energy cosmic rays, of course, the GSA cutoff was originally measured to provide a test of Lorentz Evans violation. And as Giovanni mentioned before, this has changed a little bit along the years. No? In fact, there are at present several open questions that raise doubts on the sensitivity of this highest part of this cosmic ray spectrum to LID, which is the origin of the suppression. It is related to the sources, or it is related to the propagation, which is the composition of the ultra-high energy cosmic rays, because the LID effects depend on the proton fraction. Or are there modifications in the hadronic interactions producing the air showers in the atmosphere that allow to interpret the result? The interactions of the ultra-high energy cosmic rays with these photon backgrounds, in fact, is also a source of cosmogenic photons and neutrinos. And this is another multi-messenger connection that is relevant. This plot is from Michael Reyes' talk yesterday. You see that, well, this is the expected spectrum of these cosmogenic neutrinos that are produced by interactions of ultra-high energy cosmic rays. Well, this is how, for example, this spectrum can be modified in these continuous lines in a scenario of LID. You see that the change is rather relevant. An enhancement of this peak, which corresponds to the interactions with the ABL, and a suppression, for example, of the peak corresponding to the CMB. This, of course, depends on the model that you are considering, the LID model that you are exploring. Finally, gravitational waves offer also some complementary information, and this was, of course, the case of the famous gravitational wave and GRB event observed in 2017. that provided insights on fundamental physics, the origin of these short gamma ray bursts, and constrained both LIV models and modified gravity theories. So we are witnessing this dawn of multimessenger era, with the different messengers will provide complementary information. And also in connection with this, I mentioned these first indications for a nanohertz gravitational wave signal in pulsar timing arrays, very different, that will again open a new window in gravitational wave astrophysics that probably will have implications for quantum gravity phenomenology. So the future prospects, I will end with this. There will be a number of new results and upgrades of instruments in the near future. So just to mention here a few: CTA, LASO, QG2023 COST second generation, new scattering detectors, LIGO, and other gravitational wave detector upgrades. So they will deepen in the new astrophysical windows, which have been recently opened. And the main point is that they will improve the sensitivity to the fluxes, and it will be necessary to just explore this quantitatively. So to pass really to a precision era in quantum gravity phenomenology. Well, the experimental advances will have to be accompanied by theoretical developments, of course, in the formulation of which are the phenomenological consequences of LIV and DSR models. In particular, what I mentioned about the phenomenological sensitivity to high energy scale, which is many orders of magnitude below the Planck mass. This is possible in a scenario of default relativistic invariance and may be relevant in some models where the Planck scale is not the effective scale, but it combines with further parameters of the theory. Depending on the magnitude of this low energy scale, this may be relevant even in particle physics experiments, and I think we will have some talks about that in this conference. And I want to stress here that the deformation of relativistic invariance is even conceptually very different from LIV. It lies, doubly special relativity, it lies beyond the framework of effective theory. And even the different notion of locality may be behind of some conceptual issues of DSR that I think they are not still completely solved, like this social role problem, what is called the detector problem. Well, finally, these LIV and DSR scenarios give different phenomenology for the different multi-messengers, so a multi-messenger analysis will be necessary to distinguish them as explanations of anomalies. And the cooperation between different communities will, of course, will continue to be relevant for that. So this is the end of the action, but I hope this is not the end of this cooperation. In fact, my view is that the action, what it did was to put the necessary seeds for this cooperation that will be important in the near future. Thank you very much.
We have time for a couple of quick questions. We may give priority to the conference in Nijmegen, if there is any.
Any questions here? There is one question here.
Yes, go ahead.
Well, my question will be the following. Whether it is possible to describe double special relativity within the standard formalism used within the Lorentz symmetry breaking. Because as far as I know, in many cases, the double special relativity describes breaking of Lorentz invariance, but in another language, in language of dispersion relations. Dispersion relations can be derived from some certain Lagrangians. What is your opinion about this idea, this similarity of approaches?
Yeah, so double special relativity contains an essential ingredient beyond a modified dispersion relation. This essential ingredient is the modified composition law. In fact, I would say that even at the beginning of DSR theories, more weight was given to this modified dispersion relation. I think the essential ingredient is a modified composition law. One can even have DSR models which have the standard dispersion relation of special relativity, but do not have, I mean, they contain necessarily a modified composition law. So this is something that distinguishes completely the LIV scenario and cannot be described. So that's why they are conceptually different and also phenomenally different. There is not a common framework for them.
Any other questions here? No? So we can hand it back to you. So no other questions from Nijmegen?
Yes, so is there any quick question from here? Yes, there.
When you contemplate a DSR framework with a scale much lower than the Planck scale, of course you confine yourself to DSR scenarios without in-vacuum dispersion, because otherwise they would be falsified. But and then I understand, but should we not be concerned that somewhere else, not in the in-vacuum dispersion, this deformation at such low scale would, I mean, how far have you explored possible other, I know it's like looking everywhere, but is there some, or at least maybe the opposite direction, did you see some other in-vacuum dispersion would be a key vulnerability because the data have high quality, but you protect yourself from, I mean, your scenario is protected from that by not having in-vacuum dispersion. But is there some other thing that in your experience we should look at as a possible, say, pathology produced by new physics at a scale much lower than Planck scale?
Yeah, my view is that we need to look to interactions. I mean, propagation is perhaps not important, and this is a view, perhaps a new view that can be that one can have about DSR. That perhaps DSR is a new, it's a way, an effective way to take into account, for example, a loss of locality of interaction. So in this sense, yeah, of course, the effects, you see some differences with respect to special relativity, only with the energy, one of the energy which is relevant is of the order of this lambda, this high energy scale. For much lower energies, you don't see anything. So yes, in some sense you lose this predictive power if this high energy scale is very large, but in the other, because well, one could have deviations from special relativity at energies which are attainable at present, and you don't have constraints.
Okay, so I think we have to close.
Yes.
Yes, sorry. One last quick question from here, and then we close. Sorry, I didn't see.
In other fields, like when in the searches for dark matter, there is people are plotting a plot of mass and cross sections in different experiment, different tests, are putting limits, and I would have hoped that this is not a question, it's a call for what this community should do. If you take something very simple like this dispersion relation correction, plots like this, combining different data from different experiments, and take them seriously. Take them seriously, meaning that if there is some region which is ruled by one experiment, and you want to suggest an effect in from, let's say, a threshold barrier, but there is a region in a region which is ruled by other experiment, don't suggest.
Yes.
So I think that, yeah.
Sorry, it's a very interesting idea. Is that you see, even for example, in this also from dark matter, there are regions which are excluded by some experiments, but there are still some, for example, these gamma regions, which are inside a region which is excluded by other experiments, because you can always find some way out. For example, in this case, you can have interactions with different nuclei. So if the experiment is not exactly the same, it's not considering the same kind of interaction, you can always go back. Or for example, in the case of action plots. In action plots, there is the action band, which is the preferred theoretical model for actions. But of course, one can go beyond that and say, okay, perhaps we don't have real actions, QCD actions, but we have action-like particles. And when you open this, you need then to explore different regions. So it is not I would say it is not as simple as to consider that this is, for example, cosmology. Cosmology can rule out several regions, but still you need to explore this experimentally, because there may be some caveat in these arguments. So I think the idea is very interesting to have these plots with different bounds. But I would say, yes, one has to take it seriously, but also cautiously.
Okay, so we really have to close the session here. So thank you to the other conference. I think this was a very nice and successful experiment. Yes, and okay. Thank you to everyone.
And a big thanks to all the speakers for the morning session once again.